Now I would like to show you something that is very important to understand, namely that different preparations of quantum states can actually lead to the same density operator. Let me just give you three different scenarios. So imagine that I'm going to give you a qubit, and I'm going to tell you that I'm going to prepare this qubit in three different ways. And I ask you to guess which particular way I was using to prepare the qubit. So they're quite different. Those preparations are quite different. So the first one looks like this. I toss unbiased coin. With probability half, I prepare state 0 of the qubit, and with probability half, I prepare state 1. So state 0 and 1 are equally likely, and I'm just going to give you the qubit, and it is indeed either in state 0 or in state 1 with equal probability, but you don't know which one it is. So from your perspective, you have a lack of knowledge about the preparation. All you know is the procedure that I described to you, and therefore you say, well, essentially what I have is an ensemble here. With probability half, I have state 0 of the qubit, and with probability half, I have state 1. So that gives me the density operator, the half of the identity, and this is the operator that I can use to make all statistical predictions when it comes to performing any operations, any measurements on the qubit. Now, then I tell you that my second preparation number 2, is such that with probability half, I prepare state plus, and with probability half, I prepare state minus. So state plus and minus are two eigenstates of sigma x operator corresponding to eigenvalues plus 1 and minus 1. So you can just, for the record, plus minus state 1 over square root of 2, and those are state 0 plus minus 1. Again, you are getting either state plus or state minus from me with the same probability. So from your perspective, you say, well, I have with probability half state plus, and with probability half I have state minus. Therefore, from my perspective, all I can say about the state that I'm getting is that it's described by the density operator, which is half of the identity. And again, all statistical properties of the measurements that I'm going to perform on this qubit will be described by this density operator. Okay, and there's then the third preparation where I get an entangled state of 2 qubits. So I prepare entangled state, say state omega, which is 1 over square root of 2, 0, 0 plus 1, 1. Okay, and then I'm going to give this qubit to you. So I'm going to keep one qubit, but give another qubit that is entangled with my qubit. I'll give it to you. I don't perform any measurement on this qubit, but I tell you what I did. So then you knowing my description of this preparation, then you will say, okay, fine. In this case, what do I know about the preparation? All I know that you took entangled state omega, and then that you gave me a one subsystem. So the density operator associated with the subsystems is partial trace. I trace, say, over, let this be qubit A and this qubit B. So I trace over A. And when I do all this operation, I get half of the identity as well. So here we have a situations where we have 3 very different preparations, right? But when I just present a qubit to you, all you can do is to associate the same density operator with each preparation. And so that means that no matter how hard you try, you will not be able to tell the difference between the 3 preparations. If I don't give you any extra information, then you simply don't know which way I was preparing the qubit. So you don't know whether it was preparation 1 or preparation 2 or preparation 3, because all you have access to, all your statistics are based on the density operator of the that you associated with the qubit. So in this case, we have a situation where you simply cannot distinguish which particular preparation was which way I prepared the qubit. That's actually a very important thing to know and to remember, that different preparations can lead to same density operators. Density operators is some kind of a weird mix of both a real factual situation about the state, whether it's state 0 or 1, plus your knowledge which one it is. So we weighted projector on 0 and projector on 1 with respective probabilities. So if, of course, if you vary those probabilities, you may vary the density operator, and then you may be able, in some cases, to tell the difference. But essentially, in order to be able to tell the difference between two preparations, they have to have different density operators associated with them.